So yesterday we looked at 4.3 and we practiced solving equations like that. And the goal was to eliminate the denominator. The problem with that approach, if we want to solve an inequality, is we multiplied both sides here by something with a variable. When you solve inequalities, there's a certain type of number that if you multiply both sides by it, you're supposed to do something. Does anybody know what kind of number I'm talking about? Yeah?
Negative.
A negative. If you multiply both sides by a negative, when you have an inequality, you're supposed to take the sign and flip it. Well, if we're multiplying both sides here by things with variables, I have no idea if that's negative or positive. It depends on what the variable is. So multiplying both sides by a variable will not work to solve an inequality. It'll work fine for an equation, and that's why we did it. But it won't work for an inequality. So, when we have a problem like this, all we're going to do is solve it and graph it on the calculator. Okay, that's going to go into y1. And that's going to go into y2. So let's put that in, and let's see what it looks like. Okay, y2 is going to be a horizontal line at 15. y1 is going to be some type of graph. We're looking for where the graph is above or equal to the horizontal line. To type that in, you will need parentheses around the numerator. So x to the fourth minus 3 x cubed is 2x squared. So that's exactly what you need to type in. So my calculator is set up for a standard window. What should I set my y max to?
Probably 15.
It's got to be at least 15, or I'm not going to see a horizontal line at 15. Since I don't want 15 to be right on the very edge of the screen, I'm going to set my y max to a little bit more. Okay, I'm going to go 20. I'm going to hit graph and see how that looks. Okay, let's look at that. What number can't you plug in for x in this problem? Because it would cause you to divide by 0. 2. So, when you have a number that makes the denominator 0, that creates a what? We do it as a dotted line. Or we show it as a dotted line. A what? So because 2 makes the denominator 0, we have a what at x equals 2? Yeah? Yes, we have a vertical asymptote. So let's draw a vertical asymptote at x equals 2. And if I put that in right there, what I want to do is I want to make it I'll make it a little thinner. So there's my vertical asymptote. Will my graph ever touch that dotted green line? No, we'll never touch it. So the question is, where are we above the red line? Well, are we ever above the red line down there? No. So we don't have to worry about that part at all. Are we ever above the red line anywhere else? Yes. There's 2 separate pieces at the top where we are above the red line. Is it above or equal? above or equal. So there's this piece, which keeps going up, and then there's this piece, which is just going to keep, I curved it a little too much, but it's just going to keep going up that way. First thing we want to do is find those two intersection points. Okay, let's start with the one on the left. So second calc, intersect. Move your cursor until you get it up there, but try to put it closer to the one on the left. Okay, so that's my first intersection point, 2.22 for an x value. That's, just get rid of this so you can see it better again. That's as far to the right as I can go in that section, 2.22. How far to the left is that line going to go? It doesn't keep going to the left forever because it runs into that vertical asymptote. So how far to the left does that blue line in this section go? Yep.
2.001.
Yeah, it goes right up to 2, not including it. So this, the part that's above 15, is between 2 and 2.22. Or, and now there's one other part. Well, look at this part. It's just going to keep going off like that. How far to the right is this section going to go? Infinity. This section right here is just going to slowly keep going to the right. It's never going to run into another vertical asymptote. It's just going to keep heading to the right. So, as far as how far that one goes to the right, it never stops. But the lowest value is right there. That's as far left as that section will go. So I need to find an intersect one more time. So find the intersect. And the lowest value in this other section is 2.68. I put a bracket because it is okay to include that value. Because it said right here, it was okay to equal 15. It didn't say it had to be above 15. It could equal 15. And at 2.68, we are exactly equal to 15. Just put it over here so you can see it better. And that's your answer. That's how you solve an inequality on the calculator. So it involves usually finding at least 2 intersection points. Okay. Any questions on what we did for that problem? One thing is you always want to make sure you zoom out enough. If you didn't zoom out enough, you would have never even seen this part way up here. So just zoom out enough so you see it. And that's it for 4.3. So, from 4.3, just going to cross this out because you guys did most of that last night. Let's do 13 and 22. Okay, so that's the first part of tonight's homework. Make sure you write those two down. Page 244. 13 and 22. It's 2 of the problems I got rid of yesterday. Okay. Does everybody have part 1? Okay, so now let's take a look at 4. All right, so 4.4. That is on what we call radical functions. And that's why I use my radical font. It's pretty cool, huh? Not really, no. Okay, so radical functions, section 4.4. So we're talking about things that have roots in them, like square roots, cube roots. Those things are called radicals. Here's a couple examples of radical functions. This one is a square root. Square root of x minus 2. You know it's a square root because there's no number right there. Technically, for a square root, you could write this. Nobody does that. But you could. That means square root. If you want to do any kind of root other than a square root, you need to put a number in that spot. Does anybody know what kind of root this one is? This is not a square root. That 3 makes it something else. Yep. That's called a cube root. And there's some other stuff with it, but the point is it has a root in it. That makes it radical. Another name for this is called a radical symbol. It's also called a root symbol, but you can also call it a radical. So, any expression that has that symbol with a number in this spot and then something under it is called a radical. So, the cube root of 27. That is a radical expression. It's not algebraic because there's no letter in it. But that would be considered a radical. Now, this thing right here, this number, I showed you guys an example with a 3. That number is called the index. The index can't be anything you want. First of all, the index has to be positive. It has to be greater than 1. And it has to be an integer. You cannot do the 3.5th root of 10 and have that be called a radical expression. That's a little, you can do that, but that's a little bit, it's different. We don't take 3.5th roots. Right? You can do a cube root, you can do a 4th root. There's nothing in between. So this number always has to be positive, and it has to be a number that's not a fraction. It's called the index. This entire thing is called a radical expression. This, the part that is underneath the radical sign, is called the radicand. Radicand. So the thing that is underneath the radical sign is called the radicand. In this problem, the radicand is 27. In this problem, the radicand is x minus 2. So just a few terms that you're going to see pop up. Index, radical sign, radicand, and radical. Does anybody have any questions on what those different words mean? Okay. If there is no index, if you just write something like that, we always assume that that is a square root and it has an index of 2. So square roots never put the number in for the index. They leave it blank. Now, anytime that you write something as a radical, like let's say I wanted to do this on my calculator and I didn't have the radical button, I could still do it. Let me show you how I could do it, and then let's see if you can kind of generalize the pattern. So if I had the square root button, all I have to do is do second square root 9, and I get the answer. But if I didn't, I could do this. 9 to the 1/2 power. And it's not just a coincidence that it worked, it would work for any number. Raising something to the 1/2 power is exactly the same as taking a square root. Doesn't matter what it is, just an example. If you want to know the square root of x minus 2, you could just raise that to the 1/2 power. And that's the same as taking a square root. How about a cube root? It doesn't matter what the radicand is. But does anybody have an idea? If you didn't have a cube root button on your calculator, what power do you think you could use? And it would take the cube root for you. Yep.
1/3.
You could do 1/3. So like if you wanted to know the cube root of 64, and you said my calculator doesn't have a cube root button, okay, take 64 and raise it to the 1/3 power. About a 5th root. What exponent do you think you would use if you wanted to take the 5th root of something? So we did a 2nd root, we did a 3rd root. This is a 5th root. Yeah?
1/5.
1/5. That leads us to that. We have x to the 4th, that was the radicand. And we changed the 5th root to a 1/5 power. This example right here is the whole reason why you would do that. Now you have a power raised to a power. That's from Algebra 1. Does anybody remember when you have a power raised to a power? What do you do with those two numbers? Yeah? You multiply them. So 4 times 1/5 is 4/5. So changing a radical to an exponent gives you a way to simplify a problem when you have more than one exponent. You can combine the exponents together using rules from Algebra 1. We don't do that a lot, but it could come up. Questions on that? So you're going to see in some of the problems in the homework, they're going to ask you to solve for what's called the principal root. Because we know when we take roots, for example, square roots, there are two answers technically. The square root of 25 is 5. And what other number? -5. When they say principal, what they're really getting at there is they want one answer. They only want one. So the way you find the one answer that they're looking for depends on one of two things. Is the index an odd number or is it an even number? If it's odd, what you're basically doing is solving this kind of equation. For example, x cubed equals 64. If I wanted to find the principal root to that problem, I would take the cube root of both sides. Take the cube root, take the cube root. Cube root and cube cancel. And I get x equals the cube root of 64. So if you have an equation set up like this, where n is a number and a is a number, to solve this problem, you're going to have to take a root on each side. What kind of root? Depends on what kind of number. That was a 3, so I had to use cube root. If that number was a 2, like x squared equals 25.
I apologize for the interruption. Thank you.
So if that number was a 2, it would say something like x squared. And how do you get rid of squaring? What's the opposite of squaring? Square rooting. So any equation like this, you're basically going to end up taking a root on each side. So that's an example where n was odd. Now, in this one, where I had x squared equals 25, technically when you solve that, there are two answers, 5 and negative 5. I only want the answer when I say principal that is non-negative. I don't want the negative answer. That's what that's saying. It's also saying that the thing you take the square root of has to be greater than or equal to 0. Because what would happen if I had this? If you tried to solve this one, what would happen? This is the a value, negative 25. It is not greater than or equal to 0. It doesn't follow what should be happening. So we should never have anything like this. But what would happen if you tried to solve that? Yeah?
We get an imaginary number.
You would get an imaginary number. Because now you're going to take the square root of both sides. Now you have the square root of negative 25. That's not what we're getting into. So first of all, the number under the root, the radicand, has to be greater than or equal to 0. And when you solve it, I don't want to know if there's a negative answer. I only want the answer that is not negative. So what if I, said x squared equals 81? How would you solve that? Yeah?
Oh, there goes that.
Yep. Do you know how to solve that?
Yeah, you would take the square root for 81.
Good. You take the square root on both sides. Square and square root cancel. Now, there are two square roots to 81. But if I want the principal root, what is the principal root of the square root of 81? 9, not negative 9. It's the not negative one. Non-negative answer. Okay, so that's what that means. Just give me the answer that would be positive. Again, that's for even roots. For odd roots, it is okay to get a negative answer. There's nothing wrong with that. But for even roots, no, we don't want the negative. So I want to look at a specific root, and I want to see what happens when we do square roots. And see how I use two different fonts there? So like smaller is like small font, and larger is a larger font. See what I did there? I'm on fire today. All right, so here's the number, and on this side I want to know the square root of it. So what's this? If you take 4 and take the square root of it, what do you get? You get 2. Did that get smaller or larger? It got smaller. So the question is, okay, does it always get smaller? Well, let's see. 18. Well, I need my calculator for that one. Square root of 18, 4.24. Smaller or larger than what I started with? Okay, smaller. So it looks like it's always getting smaller. How about 1? What's the square root of 1? Yeah? 1. Is that smaller or larger? It's the same. So that time we took a square root and it did not get smaller. All right? So maybe it either stays the same or gets smaller. Let's try 0.5. Square root of 0.5. 0.71. What happened that time? It got larger. Square root of 0.2. Let's try that one. 0.45. What happened there? Got bigger. So whether or not when you take a square root it gets bigger or smaller, the answer is it depends. It all depends on whether it's bigger than a certain number or smaller than a certain number. Does anybody know what number or have an idea?
1.
1. If If you take a square root of a number bigger than 1, it's going to get smaller. If you take a square root of a number that's smaller than 1, not negatives, don't go negatives, that's imaginary, so basically between 0 and 1, it gets bigger. And if you take the square root of exactly 1, it stays the same. So that, if we graph that, it leads us to a few different things that always happen with even roots. Let me show you how to graph even roots, and you'll see why these things are true. First, I'm going to do a square root. I'm assuming everybody knows how to do square root. Which is second, and then the x squared button. There's no button for 4th root, 6th root, 8th root, any other root. To do a 4th root, this is how you do it. Press the number 4. Press math. And then go to option 5, which has a little x, and then the root symbol. What it'll do is it just filled in the index for the root. I typed the 4, and then I pressed the root symbol. And now it's put in x. Let's do a 6th root. 6, math, option 5. So that's a square root, a 4th root, and a 6th root. Let's graph them all and see what they look like. So there's your square root. There's your 4th root. And there's your 6th root. Now, it just looks like a bunch of stuff overlapping. I can't see what's happening near the origin. But what I can see is it never goes into quadrants 2, 3, and 4. So then, let's zoom into quadrant 1. Make that a little bigger. And see if we can see what's happening. Okay, so there's my square root. There's my 4th root. And there's my 6th root. So let's look at all of these. First of all, it looks like they all go through a certain point. And they do. They all start at the origin, 0, 0. And they all go through the point 1, 1. 0, 0 and 1, 1 are 2 points that are common to all even roots. They all go through the origin, and they all go through the point 1, 1. Now, the domain is how far left and right it goes. It never went out of quadrant 1, and it starts at the origin. The origin is at 0. And it goes to the right forever. It never stops. So if it never stops, what do we use for a symbol? Infinity. So the domain for this problem is it starts at 0, and it goes to the right forever. And the range is the same thing. It starts at 0, and it goes up forever. Which one looks like it's curving up the fastest? The square root, the 4th root, or the 6th root? The square root. They all keep curving up. Don't think that it ever flattens out. It doesn't. It will just keep curving up, but it's slow. So it goes up forever, but it never reaches an upper limit, so that's why we put a parenthesis. Okay? So that's something that's common to all even roots. Let's take a look at odd roots, but let me graph them first. So let's do a cube root. And let's do a 5th root. I think once you put that symbol in, you can change the number without having to go back in the math menu. Okay, so you saw what an even root looks like. Even roots always have this pattern that they start in one spot and they curve like that. Now, you can flip it. And does anybody remember what symbol do we usually see in an equation? And that symbol causes your graph to flip. a negative. Depending where you put the negative, you could make this square root flip different ways. If you put a negative in front, that's a vertical flip. So it would make your square root look like that. If you put a negative inside, that's a horizontal flip. That would make it flip left to right. So then your square root would look like that. And if you did both, a horizontal and a vertical flip, it would look like that. So square roots always have this kind of curve, but it can curve to the right, it can curve to the left, depends if you flip it. But that's the general shape of the square root function. It starts at one point and goes in one direction only. Only one direction. Let's look at cube roots. I'm going to do zoom 6. What's the first thing you notice right away that looks very different between a cube root, or like an even root, and an odd root?
Starts all the way from the outside.
Yeah, it goes in both directions. It goes in both directions. Odd roots always go left and right forever. And if I zoom in a little bit, let's zoom in right near the origin. I want you to see if you can see a point that they all go through. That's a third root. And there's my fifth root. Okay. Anyone think they see a point that both of those go through?
0.
Yeah. 0, comma what?
1.
Up here?
0.5.
0, comma 0.5. So that would be right there. They don't, this blue one never goes through that black point. It's curving away from that. Anyone see another point? Yep.
0,
0,
0.
0. So they do all go through the point 0, 0. But there's another one. Yeah.
1, 1.
1, 1. Yep. And there's another one. Yep.
-1, -1.
-1, -1. Now, I know I only graphed 2 roots. I did a third root and a fifth root. But if I did a third root, a fifth root, and a seventh root, the seventh root would also go through those 3 points. So odd roots share 3 points. -1, -1, 0, 0, and 1, 1. Now, when I say all these roots share these points, we're talking about the basic case. If you do something like this, well, now you've messed up the points they share, because this is not the basic case anymore. This is a square root that's been shifted up 2 units. So if you start playing around with shifting the graph up, down, left, and right, you're going to shift all these points to other spots. But I'm saying if you don't do any of that, those are the points that are common. Now, how about left and right? How far left and right do these graphs go?
Infinity.
Yep, and how about up and down?
Infinity.
As the high, what's the low?
Infinity, negative.
Yep, they're all going to go from negative infinity to infinity. They go left and right forever, but they go up and down forever. Doesn't look like it's going up very fast, but it is going to keep going up. So that's why the domain is negative infinity to infinity, and so is the range. So those are some of the characteristics of odd roots. So we've looked at this a couple times. I think this is one time I paused the video and went back to a lesson we had done earlier. And you can transform these functions, just like every function we've studied, whenever you add or subtract inside the function, does anybody remember what that does? If you add or subtract inside, it's a certain type of shift. Anybody remember which way? Yep. It is left or right. Positive is left. Negative is right. I don't really have enough room to fit that in. But A controls movement left and right. Now D is still a shift, because any adding or subtracting is a shift, but D is not. Oops, I think I did that backwards. Sorry, let's fix that. Negative is, hold on, let me think. Left, oh, I think I had it right. Probably because it's the opposite of what you would think. It's the opposite of what you would think for a number line. So negative numbers normally go to the left. Like if you think of a number line, I'm just thinking it through. That's how a number line normally looks. So you would expect, oh, positive goes to the right. No, positive will shift you to the left. Negative will shift you to the right. So it's the opposite of what you would expect when you look at a number line. It's just that's how it is. Now D is a shift as well. But what direction do you think D would shift you? Yeah? Up or down, and that one is what you would expect. Positive is up, negative is down. B and C are stretches. A was a horizontal shift because it moved me left or right. B would be a horizontal stretch. Now C is still multiplication. There's no dot here, but pretend that it's multiplication. But it's on the outside. Just like D is on the outside. D is vertical, but it's shifting vertically. C is stretching vertically. Multiplication is always a stretch. Addition or subtraction is always a shift. So that's a vertical stretch. If C was negative, that would cause a vertical flip. If B was negative, that would cause a horizontal flip. But that's what the A, the B, the C, and the D do. And the reason I use those letters is because that's the order that it does what it does in. First it moves left and right, then stretches left and right, then stretches up and down, then shifts up or down. Yes? Yeah. So let's try an example with a square root. It's not going to have every single letter in it. This problem only has one. And all I want to know is if you started with the square root of x, how would you get the square root of x minus 2? So you need to tell me what the minus 2 is going to do. So first, how many transformations are happening in this particular problem? Yep.
John.
It's just one. There's only one thing happening. And what's the minus 2 going to do? Is it going to stretch it vertically by a factor of 2? Is it going to stretch it horizontally? Is it going to shift it left or right, up or down?
Is it going to shift it to the right too?
It's going to shift right to yes. So to get this one from the original, shift the square root of x right 2. So to get the new one, shift the original right 2. How about that one? To get h of x from the original, what would you do? Yep, right.
You moved to left 3?
Yeah, move it left 3. The plus 3 is going to shift it left 3. So shift square root of x left 3. So that was 1. That was the second one. Now let's look at this one. What's strange about how that one is written? If you compare that one to my example up here, what's different about how I wrote it and how this problem looks? Yeah.
Because the x and the number switched.
The x and the number are switched. You're supposed to put the x first and the number second. So let's fix that. And now, how many transformations are happening here? Yep,
2.
there are 2. The 3 is going to do something, and then the negative is going to do something. We talked a little bit about what the negative does. So to get k of x, step 1. What would be the first thing you would have to do? And if you forget the order, look at the letters and look at A first, then B, then C, then D. What would happen first here? Yep.
You should left 3.
You're going to shift left 3. Second thing is what that negative is going to be. That's a negative where B would be. So it tells you what kind of thing is going to, whether it's going to be a horizontal or a vertical. You just have to know what the negative does. Yeah? That's a horizontal flip. Horizontal flip means this. If you had the letter D, that's a horizontal flip. It's a flip left to right. Horizontal. Vertical is flipping up to down. Okay? So that's a horizontal flip. Or you could say horizontal reflection. Either way. Okay, any questions on that idea? Now what if it had a +5 on the end? What would you say the +5 does? That would be the third thing we would have to write, yeah? Yep, shift up 5. Good. All right, so I think the last thing we'll look at today is how do we sketch a radical function. Okay, we'll probably do one sketch today with an even. We'll do another sketch tomorrow with an odd. So that we'll pick up with sketching tomorrow. So the first thing that you want to do is find the point that normally would be at the origin. For an even root, it looks like that. I call this a start point because that's the point that it starts at and it goes in one direction. For an odd root, I call the point at the origin a center point. It's a center point because that's the center of the graph and it goes in each way from that point. So in odd roots, call the origin the center. For even roots, I call the origin the start point. It starts and curves one way. Either way, whether you're doing an even root or an odd root problem, you want to figure out what that point is. So if you shift something left, right, up, or down, you want to figure out where the new start point or center point is for your graph. And then we build from there. How do you find the point that used to be at the origin? Well, a coordinate has two values to it. It has an x value and it has a y value. To find the x value, take the radicand that's the thing under the root, set it equal to 0. That will give you the x value. Once you know the x value, we can plug that number back in to find the y value. So we're going to use substitution. We're going to plug it back in. What that'll do is it's going to give you the start point if it's an even root, or the center point if it's an odd root. Now, for an even root, how many directions does an even root go? Does it go in one direction, or does it go both?
One.
It only goes in one. So once you get that start point, let's say maybe it moved to the right 3 units, you only want to check points on one side of that, because it's only going to go one way. It doesn't make sense to check when x is 0, -2, -3, -4. There aren't going to be any points over there. So for an even root, you're only checking points on one side of the start point. It could be right, it could be left. For an odd root, we're going to check both sides. Okay, because odd roots, if you have the center, you might get some points like this. You might get some more points like that. And then you make your sketch. So odd roots, yeah, you got to check both sides. Even roots, just one. So let's try sketching this odd root. Let me type it in. You don't have to type it in right away, but you're going to need to eventually. So to type it in, you need 2 times 3. This 3 is not 2 times 3 is 6. This 3 is about to become my index on my root. Math 5. So 2 times the cube root of 3 minus 2x plus 1. Make sure the plus 1 is outside the root. Okay, what do we set that equal to find the x value of my point? What do we set the radicand equal to? 0. Set the radicand equal to 0. Add 2x. And what do I get for x in this case? Yeah.
Would be 3 over 2.
3 over 2, 1.5. Now to find the y value, plug it back in. Let's plug 3 over 2 in right here. What's 3 divided by 2 times 2? We're plugging that number back in right here. And we're going to get the y value. So what's 3 over 2 times 2? Yep.
3.
3. What's 3 minus 3?
0.
0. What's the cube root of 0?
0.
0. What's 0 times 2?
0.
0. This is basically your y value every time. It's the number that's at the end over here. Because that whole part is going to come out to 0, because that's what you just did on purpose. You set it equal to 0. This is an odd root. For this problem, am I going to get a center point, or am I going to get a start point? Keep in mind, it's an odd root. Center point. So my center point is 1.5, comma, 1. That's the center. So what we'll do tomorrow is we need to graph a few more x values. We'll use the calculator to figure those out. And that'll give me my sketch. Okay, so homework for tonight. Let's see, 5 and 6. Those should be fine. those two for tonight. That's all we're gonna do. I'm just gonna change this. 5 through 10. So homework tonight is 5 through 10 on 250.